I would like to introduce our next speaker, Peng-Jun Ju from University of California, Riverside. He will be presenting on characterizing transnational internet performance and the great bottleneck of China.
Hi everyone, my name is Peng-Jun Ju. I am a PhD candidate at the University of California, Riverside. The talk I will be presenting today is titled Characterizing Global Transnational Internet Performance and its Bottleneck. This is a collaboration with University of Michigan and Tsinghua University. Growing up in China, I have been satisfied generally with the internet speed and reliability. We have very much all the services you can find in our domestic network. For Google, we have Baidu. For Facebook, we have WeChat. But since I started to apply for application for US grad schools, I noticed the speed is really slow. Sometimes it was so slow that my submission failed. It occurred to me that I rarely visit foreign websites, but there are services that haven't had a Chinese replica. For example, GitHub, Overleaf, and the speed is also very slow. This observation made us wonder if this phenomenon is unique to China. We think this is a rather important question because transnational network performance is an indicator of economic development, infrastructure investment of the countries, and it allows the information to flow around the world. We also want to know what we can do to help improve the performance. So our measurement wants to look into traffic flows across national borders all over the world. What is the throughput? How often does the slow speed happen, if there is any? And what factor influence transnational performance? Here is our first measurement. First, here's a map of our vantage points. We have 61 vantage points in 29 countries and regions that cover all 6 continents. For each country, we have 2 vantage points on average. There are either a cloud server, red here, or a residential host, blue dots here, provided by volunteers. This figure shows our experiment setup. We host a HTTP server on every cloud server and let them download file from each other, like this session. A residential host are always behind NAT, so they can only download file from all the cloud servers. We kept the speed at 4 megabits per second to avoid wasting unnecessary network resources. Here are the answers. Here, this figure is a box plot on the global transnational throughput. Here we call the one end of one pair who send the data sender and the other receiver. For example, China-others means other are sending data to China, which is the downstream of China. For the rest of the talk, we use China to refer specifically to mainland China. This is a box plot, so the size of the box indicates the variance of the data. In our case, the smaller the box, the more stable the throughput. The horizontal line indicates the median, and the dot indicates the mean. As you can see, the box of the downstream and upstream of African countries and the downstream of mainland China is very large, and their mean is only around 2.5 megabit per second. Good news is that the box of the rest of the world, the countries, is pretty small. which means that their traffic across national borders is fairly stable. So for most countries, their transnational network is pretty good. Although both African countries and China suffer from unstable throughput, their features are different. African countries experience slowdown on both directions, while China interestingly only experienced it on one direction when data was entering China. Surprisingly, China's upstream is fast and stable like the rest. Another unique feature of China's transnational network performance is that it has a much clearer diurnal pattern. These three figures are the downstream throughput of Nigeria and Egypt and China with the same sender. In the last figure, we can see shortly after 8 a.m. local time every day, the throughput starts to dip and stays below 500 kilobits per second. It recovers swiftly at night between 1 and 2 a.m. The transnational network performance in China is intriguing. However, so far our measurements included only a small number of vantage points in China. We are not sure if this observation is a random incident that we happen to capture. So this prompts us to perform additional experiments to examine this phenomenon. So our next measurement is about China's transnational network. We try to answer these three questions. I will cover them one by one. First question would be, how widespread is the phenomenon throughout China? Is it happening only in specific locations? Is it happening only in specific time? Does a similar slowdown occur for domestic traffic? Does it apply to real-life web servers? To increase the space coverage, we include more vantage points in China to 17, as you can see in this map. To increase the time coverage, we repeated the test 4 times with fairly long duration. This figure shows our end-to-end experiment setup. Since we only observe slowdown when the traffic goes into China, so we make all vantage points outside China as senders, and the one inside China as receivers. In our global measurement, domestic traffic was not measured, so we included here by making the domestic VP of crowd servers as senders too. Let the receivers also download the file from domestic senders. To depict the real-life usage scenario and also eliminate the potential caused by something wrong with our own HTTP servers, we pick the top 14 unblocked websites. All 8 of them are foreign and hosted outside of China, and 6 are domestic. We find a sufficiently large file on each web page and repeated downloading the file. All receivers resolve the domain names of the websites locally. So the answer to this question is the slowdown is prevalent in almost every city. So here is an average slowdown hours per receiver aggregated over all its corresponding senders. As you can see, most receivers experience on average 5 to 17 hours of slowdown per day. The slowdown is prevalent on every senders as well. This figure is the average slowdown hours per sender. All suffer from 4 to 8 hours on average daily. Hong Kong is an outlier because it has the least slowdown hours. Here is the CDF figures of the average slowdown hours per day across 5 tests. The result is consistent. As you can see, the lines are really close to each other. Roughly 70% of the pairs have a slowdown period of 5 hours or longer. And the result of top Alexa test is consistent with other tests. The purple line here is the top Alexa test. And here is the aggregated number of slowdown hours experienced by all receivers per website. Generally, the magnitude of slowdown is high and comparable to the end-to-end experiment. The reason why Apple experienced almost no slowdown is because Apple has a server located inside China. This figure also demonstrates how important it is for a foreign website to host their server physically in China. In contrast, there is no slowdown in domestic traffic. The domestic domains shows no slowdown at all. Now we confirm the existence and prevalence of the slowdown. We want to know more about it, which motivates us to the next question: what are the performance characteristics? So what factor influence performance? The first feature is that the slowdown follows a specific diurnal pattern. For example, in figure B, the slowdown starts early in the morning from 6 a.m., lasting all the way through 3:30 a.m. after midnight, lasting a total of more than 21 hours per each day. However, not all slowdowns share this only one diurnal patterns. Actually, different location pairs might have different diurnal patterns. Beijing and Sweden might have one pattern. Beijing and Japan may have another pattern. For example, here figure A has a different pattern. Another thing that's worth noting is that May 1st and May 2nd are the national holidays in China, and October 1st is the National Day and China's 70th anniversary, which means the slowdown is not affected by the important national day or holiday or weekend. In our last experiment, we control both ends so we can capture the raw packet trace to get the loss rate and latency. When we expect the end-to-end loss rate from the raw packet trace, we find that most packet losses occur in one direction only, from foreign country entering China. This matches the observation we had in the global test, where the throughput is low only when the data is sent from outside into China. The average loss rate over an entire day is typically in a range of 5% to 15%. From the end-to-end test, we observed high correlation between low throughput, increased end-to-end loss rate, and increased latency, as you can see here, which is generally in conformity with a normal congestion. However, this is not to rule out the possibility that the congestion can be artificially imposed, for example, by lowering the bandwidth. So we try to ascertain whether the observed bottleneck is an artifact of some traffic differentiation policies. For example, is it based on protocols? Is it based on protocol types, packet types, or speed? We performed a number of A/B tests. We found no noticeable differences between all the A/B tests. Our next question is, where is the bottleneck? Before that, I want to give you a bit of background on China's unique network topology. A recent report from Oracle claims China's network is like an intranet. First of all, China disallowed foreign ISPs to operate within the country, and only recently lifted the restriction. Also, the report claimed that China is connected to the rest of the internet primarily through a limited number of connection points, which are always physically located outside of mainland China. Here is a figure from the report. As you can see, all the connection points are physically located outside of mainland China, and most traffic passes through the United States and Western Europe. Our result shows the bottleneck mostly occurs within China. The detail of how we locate the bottleneck can be found in our paper. We characterize the bottlenecks hops into 4 groups. We found that 71% of the cases, the bottleneck hops are located deep in China, which is abnormal because we know the domestic infrastructure can handle the domestic traffic pretty well. However, it fails to handle the smaller transnational traffic. And it does not make any sense from the economic perspective, as it is much more expensive to construct transnational links such as submarine cables, which are interestingly often not the bottleneck here. So here is a summary of our current findings. The slowdown is surprisingly prevalent in almost every country, happening every day, and it occurs to top Alexa website as well. And the domestic traffic, surprisingly, is very stable, doesn't suffer from slowdown at all. The packets are lost only from one direction, going into China. And the slowdown follows some interesting varied diurnal patterns. And we found no irregular traffic throttling policies. And the bottleneck almost always occur within China. Now we come to the third question, where are the causes? We come up with 2 classes of hypotheses. First, the slowdown can be due to some government regulation, for example, serving the purpose of censorship. Second, the slowdown can be due to financial motivations of the Chinese ISPs, attempting to make a profit of it. International peering. As we covered earlier, there is no sign of traffic differentiation based on protocols, even the ones that can bypass the censorship. As China is known for its advanced censorship capabilities, it is natural to suspect it has something to do with the slowdown, especially when the slowdown patterns are so diurnally regular. One possible explanation is that GFW is very sensitive in processing large volumes of national traffic and can become overwhelmed easily. However, GFW operates as an on-path system, which only processes copies of existing packets without the ability to discard existing packets. In addition, we designed a small experiment to locate the hops with GFW presence using TTL limited probes. and then try to match them with the bottleneck hops. We found only 34% of the cases it is matching, so it's not likely it's due to GFW. Great Canyon, on the other hand, is indeed an impact system, but we have no evidence of it being repurposed for traffic throttling. In fact, as mentioned earlier, the slowdown characteristics from the previous measurements closely matches those in a natural congestion. According to a recent report by the China Academy of Information and Communication Technology, China's international submarine cable development still falls behind the world's other major economies. However, this is unlikely to be the primary cause because, as we saw earlier, the bottlenecks are most located within China, not on the border. A more plausible reason is financial related. In the early years, Chinese ISPs do not have a good reputation of making international peering easy because they wanted to grow their own transit business and make themselves to be top-tier ISPs. According to China Academy of Information and Communication Technology report, all the 3 state-owned ISPs have set up a premium transnational network primarily for business uses to maximize their profit. For example, here is the screenshot from China Telecom Global's official website. They offer 4 tiers of services to connect to Chinese user. So the toppest one even offers static route. To verify the existence of tiered services, we found an exotic VPS provider reselling these tiered networks through hosting, and they provide test IPs that allow customers to check their loss rate and latency to these nodes from within China. We found the loss rate does decrease with the tier of network. At the end of the day, we admit that this analysis is largely a best effort based on our data and and we believe pinpointing the root cause further would require potential insider knowledge about the government policy and ISP's inner working. So here is a takeaway of our presentation. So we found the slowdown is prevalent nationwide every day, and it's happening every day and applied to real life websites. However, the domestic traffic is not affected at all and is very stable. And the slowdown follows some varied diurnal pattern, and the packet loss is only happen in one direction. The bottlenecks are mostly within China, and as to the causes, we found it is not due to some irregular traffic throttling, and we haven't come to a conclusion because it requires potential insider knowledge. So our future work is to look into more countries, to study more countries such as Russia and Iran, because we believe this is a long-term trend at a global scale. Thank you. We hope our effort can help administrators or policymakers to locate the slowdown problem and eliminate the bottleneck. Thank you. That will be all.
Well, thanks for listening, everybody. Unfortunately, we had some technical difficulties with our speaker, and he couldn't be online for questions and answers. But I'm sure if you ask on the NANOG waiting list, he can reach out and answer any questions you might have. We're going to, I did want to make a quick announcement. There's been some discussion of having some Zoom breakout sessions on Wednesday as kind of mini boss. So if that's the kind of thing you're interested in, mention it in the comments or send email or something, and we'll see what we can do. And this concludes our current session. We'll return at 3:30 Eastern with one of my favorite talks from our archives, Jeff Houston on Desperately Seeking Default. Thanks.